Thank you, John, and thank you, Ron. It is my pleasure to welcome you all at this in-person event. I'm going to be your MC for the day. We're going to just jump right in with the technical content. So the first panel is going to be about modern tools for quantitative investing. And we have three phenomenal speakers who have, amazing academic credentials, but also have practitioners' experience. We're going to have Jun Liu from Harvard University, then Natesh Pillai from Harvard University, and Panos Toulis from the University of Chicago Booth School of Business. Panos, unfortunately, had a flight delay, but our wonderful production crew was able to, we'll have Panos speak virtually for us today. So with that said, it's my pleasure to introduce Jun Liu as our first speaker. And welcome, Jun.
Thanks, Edo, for introduction and also for inviting me here. It's a great pleasure and also very impressive to first time talk in such a high room for professional talk. I would like to bring some of our recent thoughts about, just as Edo said, between machine learning, statistics, and how they play together. I don't know how you use this for financial or business, but I would be more interested in, at this point, all new ideas regarding how this is used. So without further ado, let me try this. Just the standard statements. These deep neural networks have been very influential in recent years. We have seen a lot of success stories. But it seems consensus appear to be like they're very, very powerful representers. And most of success stories we heard are essentially noiseless situations. In other words, you can distinguish dogs and cats, but humans can pretty much do that without much hesitations if the picture is not too blurred. So in some sense, we, in past years, have not been able to represent them very well, so that we couldn't come up with very simple classifiers. But with the neural network, it seems to be able to do that. So that's one of the thoughts which seems to inspire us, saying, if it's such a good representer, can we use that for some statistical tasks? That's actually the original thoughts we had. In some sense, they're not unnatural, because we have been doing this in the classical ways for many, many years since the Taylor expansions. So we basically represent function by additive terms of, say, different complexities, and for wavelets and Fourier transforms, they're always in this type of ideas. But they're not more human, more natural than neural networks in some sense, because they're just human natural, not nature natural in some. We are better at organizing the simple things. On the other hand, there seems to be artificial from nature's perspective, why they should be represented by this type of terms. We may have some heuristics why linear terms are more important than others, but anyway, that's just some thought. So we have been always knowing that the classical image of neural networks was this brain networks. So there are all these complex networks. So this is developed analogous to humans or in these real brains. In some sense, I was just thinking, like, people have been talking about optimizations. If it's really analogous to human networks, by nature, it shouldn't be able to optimize. Because you and I are so different. If we're all optimized, we will be the same. Or you may argue that we have different networks, but even within yourself, sometimes you feel you're so dumb, sometimes you feel you're really smart. So you are reaching different plateaus. So in some sense, we are always constantly changing, but somehow even local optimum seems to be good. But that's just just my random thoughts. So again, so let me just be a little more concrete on how we might use this flexible representation for some statistical tasks. So one of the classical statistical challenging problem is this measurement error models. You can put many different models under this umbrella, but the simple formulation would be, say, you have covariance X, but you can't observe that. You observe a noisy version of that. It's a W. You suppose to have a response Y is an unknown function of the covariance X with some error. The challenge would be that you don't know F. F is non-parametric. And now we assume the error terms are relatively known in the sense that, say, for example, U is normal with no variance. Empirically, you might be able to estimate that from other source. So also epsilon is also have known forms like normal 0 with some variance sigma square. So the challenge, of course, is a non-parametric F make it a little tricky to figure out exactly what's going on. So these are some basic assumptions. So there are many ways of doing that since early 90s and so on. There are some well-known names like Jianqin Fang and also Ray Carroll. So they have made their names by making important contributions towards this. They're essentially using this smoothing spline type of frameworks, modeling unknown F by linear combination of certain basis functions, and then you do some kind of iterations or extrapolations, those type of ideas. But as I said, why should you use a linear combination of some known bases? These are very artificial in some way, right? Of course, the nice part is that we can analyze additive terms a little more easily, but the representation power of that linear additive forms may not be as good as neural networks. So that's made us move towards neural networks. And also, there is, if you notice that, if you're thinking more Bayesian way, that's what I used to like, and you think about, say, X has some distributions, right? Then you can start. If X have some distributions and W will have some distributions, you can write the full joint distributions and do posterior inference. It's like a standard missing data problem. You don't observe X, you want to impute that. But the difficulty is we don't really know the distribution of X either, so we could make some artificial assumptions to start with, or do completely non-parametric. But that's another artificial part you could try. Actually, we did try. So here's the connection with neural network. It's a little bit busy, but I want to give you a global view of what we might use neural networks for. Ignore the very left one for now. So the key is the right one, which is use neural network to represent this unknown function f. So this seems to be standard, obvious way to go. And another component is, as I said, we want to represent some distribution of the prior of x. So the classic non-parametric Bayesian prior would be like the Dirichlet process, since which is typically challenging to work with and also non-smooth. So here we can use a neural network to represent that as well. But as a prior distribution, you want that to be invertible. So there's happen to be an invertible neural networks called normalizing flow you can use to represent that distribution, which is essentially transform, say, standard normal distribution random variables into some any forms you like through a neural networks, which are invertible, so you can calculate the densities and derivatives directly. So at the top of the slides, you can see we can explicitly write down the posterior distribution of everything with these frameworks, ignoring the left part. The left network is actually used to compute approximate posterior mode for this. Conceptually, once you write down the two neural networks on the right and top, you could just crank this new MCMC framework trying to do the Bayesian calculations. But you can imagine how impossible it is with so many parameters in neural networks to do MCMC. And also you can potentially do EM type of algorithms by integrating all this missing data to get the maximum posterior mode estimates or the EM estimates of this unknown function f. But then we need to integrate all this x part, which is also quite difficult. So that's where this left neural networks is coming to play. They are actually playing a computational approximation role. They are trying to approximate the E-step calculations. Don must know this. The E-step in a lot of EM algorithms is very hard to complete, especially in this case. So the general framework actually fall back to the classical statistical EM type of computations. We want to do the EM computation to find the maximum posterior estimate for this unknown function f through these neural networks. But we need to integrate out this unknown x. And in the, this machine learning literature, there's a recent development called the variational approximation or variational autoencoder. They're essentially trying to approximate E-step by some kind of important sampling using different distributions. If you are familiar with the EM algorithm, the E-step, you need to average over the missing data or the complete data log likelihood using the distribution, the conditional distribution of missing data given all the other parts. But that particular averaging distribution is hard to get by in this framework. So one of the shortcuts is to use another distribution to approximate that. This is so-called variational approximations. They are essentially, this is the EM integrals, and they're replaced, this Q function, as I said, in the EM is this conditional distribution for missing data. But we are trying to approximate this Q function by some easier functions, like a normal distribution with some mean and variance adjustable. So that's the trick people play in this business. Of course, in these large networks, even the normal distribution is not easy to work with. So that need a neural network here, which will give out this mean vector and covariance matrix through these neural networks. That give you this approximating function. So in other words, this mean, this mu and the sigma is the basic model for this Q functions, and we need to model this mu and the sigma through a neural network to make it complex enough or adjustable enough. So that's sort of the conceptual framework. The details are a little trickier, but you will need to be bothered by at this time. In any case, so that's sort of what we saw the neural network can help in this case. And there's also a trick if you're interested. It's specific to the neural network modeling for this Q function. One of the nice things about this Q function is as iteration goes on, you want to adjust its parameters so that it will approximate this missing data function distribution a little better. And to adjust that, they use this neural network trainings to update all these neural network parameters. But if you want to adjust those parameters, you have to take derivatives. One of the things people notice in this business is that if you take derivatives for some distributions, and it's better to reparameterize this in the integram. So that's a little trick. So that actually is quite important in the computation. If you notice this, if you just fix this Q function, of course you don't need the next slides. But since this Q function is being adjusted as the iteration goes on, and you sort of have to do more efficiently. The way to adjust them, as here, is to take derivative with respect to the phi, the left neural networks. But to take that neural networks, if you do this integrals through Monte Carlo, you have trouble to take that derivatives. So that's this trick. Anyway, so just show you a few toy examples. And this is a toy example to compare different ways of modeling this X and comparing different algorithms. And I can't really see. So one of the more naive methods is to directly use neural networks to model the response, ignoring the measurement error. You can see that's really bad. And also, if you don't average out the missing data, you can use joint mode. As we all know, that's bad. So we just show the green one is bad. That's the mode is maximizing jointly. But for all the others are different prior models for the X parts. This seems to be reasonable because our X is simulated from a mixture of 2 components. If you model them as mixture of 4 components, 3 components, they're all similar. And if you use this so-called normalizing flow, that's also quite reasonable. It's a little more variable because you don't really follow the exact shape. So here is another simulations to illustrate that the neural network representations indeed can adjust to different smoothness of the functions. Like in this case, we simulate part of the curve by one Gaussian process, the other part by another Gaussian process, and then we patch them together. So the smoothness is a little different, especially there's a kink in the middle. So if you use some other like classical methods that tend to smooth out, but neural networks seem to be able to more adjust it. These are just some plain estimates. So it seems to be improving upon the classical representations. Not by a huge amount, but it seems to be useful. And also very easy to generalize to high dimensions, not too high. Even 2 dimensions, the classical methods will have trouble. 3 dimensions almost impossible if you use just spline basis functions. But this neural networks representation seems to be more flexible. But of course, there's no guarantees. So here's take a little twist. This is another problem, just trying to demonstrate some of our recent thoughts. They are very early research at this point, but I thought it's interesting. So one of the classical statistical methods is bootstrap. And bootstrap is trying to say, so the most classic bootstrap is to resample the data, and then you estimate and try to represent the uncertainties of the parameters by using the bootstrap samples. And one of the twists, which turns out to be, Dang may be able to tell you that story, but it's also related to Dang, is the Bayesian bootstrap, which is, can be viewed as a smoother version of the bootstrap. Although Dang originally wrote a paper to basically try to show how non-smooth or ridiculous the classical bootstrap is, but it turns out to be much more influential than his anticipation, and many people pick up that idea. So the difference is that instead of resample the data, you actually can generate the probability vector from these Dirichlet distributions, and then you sample the data according to this probability distribution from Dirichlet. And it's like a smoother version. So you can think about our original bootstrap is 1 over n for every samples. Here, that 1 over n is actually varying according to these Dirichlet distributions. And you can also see this as a limit of Dirichlet process. But the nice thing is of this twist is that you can now think about bootstrap as a weighted sum of some log-likely functions, and then you try to optimize that weighted sum. So it's a smoother version. So that's what I wrote as theta w there. It's like you generate a w according to Dirichlet, and then you optimize that, you get the theta w. That's how you generate theta. But this one is much smoother. Actually, it's easier for us to think about in a more this neural network framework. How we use neural network? Well, conceptually, it's actually the mundane approach. You can think about you generate a w, and then you get the theta w. You generate another theta w, you get another theta w. Then you could potentially fit the function of w as your bootstrap samples get to a theta. But that seems to be a little too heavy. You have to generate a lot of training samples to get a reasonable good function. So now we thought that it's probably easier or more effective to think about optimizing one function, which we call it integrated function, by taking an average. So instead of doing for generating each W optimize this, you can actually finding a function form G, say G phi, which is parameterized through the neural networks, so that G take each W and output a theta. And our goal is to minimizing this average, this expected values, expected over this distribution of W. So you can show that if you G function optimize this, then GW actually give you the solution for each theta. And so this is actually make life much easier because you can do Monte Carlo simulations for generating W, optimizing this, and then you can adjust the neural network parameters to make this G a little bit better. So you don't really have to go through each W fit a GW, this type of framework. You can just optimize this integrative loss or integrative function to get the representation G, and this actually can give you bootstrap samples. So we did show some simple examples that works quite nicely. We also show this a little more challenging example, which is logistic regression with relatively high dimensions. And in this case, we all know the standard bootstrap will have biases, and you can do a little bias correction through different ways. And for example, the well-known ones are, for this particular example, you may not need to do the double or triple bootstrap. You have special tricks. But we just want to demonstrate that there are some class proposed ideas in the bootstrap literature doing this double bootstrap and triple bootstraps, but that's extremely time-consuming. But through the generator framework, that's trivial. You sort of just train functions, and you do double and triple bootstrap with almost the seconds. And then you can actually get this almost correct, the unbiased, like bootstrap samples. You can see the coverage. So double G, we call it GBS, generated bootstrap sampler. And you compare to this BCA, which was proposed by Brad Afrell many years ago, or ABC, he has a few such names. It seems to be better than that, but it's just very simple demonstration. So this is, I think we are still working on this. One of the challenges, of course, is the theory, how we prove this is actually working better. Empirically, we found like these three-layer networks with plenty of nodes is good enough. They're typically not overfitting. And one of the nice things about this is we even can do some convergence diagnostics by using some of the classical bootstrap sample. For example, we may generate 10 bootstrap samples and set aside, and then do these optimizations, and then use that 10 sort of bootstrap samples as testing to test your results. It seems to be a reasonable approach. And another thing we thought about is we could use this neural network formulation for empirical Bayes, but we did a little bit test. Empirically, this seems to be working, and it seems to work as well as you probably know. You can model this pi as a Dirichlet process mixture of Gaussians, for example. That seemed to work reasonably well. I won't go too much on that. But there's one thing which I thought it could be interesting for people, and also not considered by typical statistician, is that we found this, you can actually use a neural network representation to do tuning parameter adjustment or tuning parameter learning. In this case, you can think about also putting a weight to each data set. So like this, you can use this to approximate cross-validations. Cross-validation is basically giving weight 1 to a bunch of data and given 0 to another data, and then you're sort of trying to optimize. And again, you can cook up this integrated loss type of the objective functions. So for example, if you want to do lasso type of optimization, there's a tuning parameter. So I'm just giving some example in the first 2 lines, which is some generalized form of least square. So you have f is some functions, whatever you are interested in. And you have a regularization term, which is lambda and f. There could be a tuning parameter in lambda or some things. And now we can also consider some kind of distributions on one is the space of lambda, which you want to choose parameters, tuning parameters for. Another is the space of w, which is just in different sample. And then you can train this G hat by this neural network things. And at the end, you can actually, once you have this trained, you can easily get the cross-validation results by just plug in. You have this generator, you just plug in this vector, then you get the cross-validation results. Long story short, you can actually do this quite well for lasso. So you can almost reproduce exactly the same lasso pictures as they did for least squares. But for lasso, they have nice trick to actually do this cross-validation or do this kind of curves very easily. But here we just do a stupid neural network trainings and trying to approximate this cross-validation type of functions. And it turns out that you can almost reproduce this lasso, how this different coefficients come in as you're changing the tuning parameters. And also, you almost cannot distinguish this curve. This is cross-validation curves for changing the lambdas. They're almost exactly fit. The blue one is the standard cross-validation. The black one is this GPS, which is exactly overlapping with the blue one. You almost cannot distinguish. So it seems that of course, this curve is so trivial from neural network perspective. They're just very nice, smooth, convex curves. But you can see the potential could be generalized to if you have to cases where you have like 10 tuning parameters and at different dimensions. If you do Greek search, that will be crazy, and this could help in that perspective. So these are still work in progress. Just quick concluding remarks. I think it's kind of inspiring. We all love the stories, this DNN people telling us, and see all these dogs and mouse can be represented. And also the progresses in language processing is remarkable. So we thought some of the classical statistical problems may benefit from some of these representation powers. But mathematics behind all these methods are still very elusive. I don't think anyone really get a real sense of how this works, although there are some theories, mostly of them are very high level. In any case, we think this, some of these non-parametrics methods practically could be better approached by using these neural network representations. Most work is done by Ming-Su Shen, who is a joint postdoc between me and Natasha, and has been quite innovative in thinking along this neural networks and the statistics. And also some of my postdocs, Xin and Tracy. Tracy is our new faculty, and she has been also very innovative and brave to attempt on this direction. Thank you very much.